Okay. Well, first of all, I'd like to thank Dr. James Mann for being willing to give us today's talk. He is quite an impressive fellow, if I might say so. And he is currently the Alva C. Todd Director of Industrial Technology and Management and a Research Professor of Mechanical Materials and Aerospace Engineering at Illinois Institute of Technology. That's quite a long title, I even that. And President of M4 Sciences, which he helped found in 2005. He holds a BSAAE, NSE, and PhD from Purdue, and also an MBA finance degree from Indiana University. He has 30 plus publications, 10 plus patents, and as I said, he's a co-founder of M4 Sciences Corp. And he's been a visiting scholar at Purdue, and as I said, he is currently, well, he has also done many uh, academic and industrial projects. So he's also a fellow of the American Society of Mechanical Engineers and Society of Manufacturing Engineers. So that's quite a lot to take in. And so I'm going to now hand it over to, I'm going to just make you a co-host,
Thank you
James,
for the introduction, Eddie.
and let me just make you a co-host so that you can share your screen. Okay, James, over to you.
So thank you for the introduction, Dr. Robbins, and I'd like to also thank Professor Lataniason, who invited me to join all of you to share my talk this morning. I'm grateful for this opportunity and certainly listening to everyone's background, I am compelled to say that it's an honor to be with all of you, and also what an amazing group of people and accomplishments. So I feel honored to be with all of you. So my talk this morning, I'm going to share my screen, and I'm currently presenting today. I'm here at Illinois Institute of Technology in Chicago, and um, hopefully I can get this queued up so you can let me know. I hope everybody can see this. I'm going to have to change the mode. And please don't hesitate if you have a question um, along the way. Uh, you're welcome to interject. So you should see the presentation view. It's my computer is pausing for a moment. So, okay.
Yes,
Uh,
now we see it.
okay, so today I'm going to talk about machine-based deformation processing of materials and um, or materials manufacturing by machining-based deformation processing here at the Wilson Science and Technology Forum. And I'm James Mann from Illinois Institute of Technology. My computer is not responding, so now it's responded by going 3 slides deep. So I'm waiting for it to queue back, so I apologize. Try it again here. Okay, so advanced manufacturing today is complicated in many ways, and I'm sure all of you can appreciate this, that we're constantly looking for new ways to become more efficient. And today there are even more concerns around environmental impacts and societal aspects of manufacturing, developing sustainable systems. And then we're also blessed with all of the new interconnectivity with artificial intelligence, Internet of Things, smart systems, and amongst all this, trying to commercialize new technology. Industry needs historically and even today are still centered around manufacturers trying to innovate with new product designs, new processes, and a lot of these products that are on the screen right here uh, take advantage of materials that all of us, in many ways, have interfaced with over the years. Some of these materials have been around a long time, but others are evolving. But stainless steels, nickel alloys, titanium alloys, refractory metals, composites, and ceramics. And this picture or series of pictures here is just an example of just a range of different products that all of us uh, benefit from in our lives, things including orthopedic parts. You see a picture on the far right corner there. That's from Caterpillar. Obviously, that's a large excavator. Picture of a windmill turbine, Cummins fuel injector, an artificial heart from Abbott, Beckert, textiles manufactured from metal fiber. Just a whole range of products, all of which uh, improve our quality of life, but also have enormous challenges in manufacturing and materials. And so, one of these areas that is specifically what I'm going to center part of my talk around is the process challenges around high performance materials when they're in a format that is in a sheet or strip or even wire shape. There are issues around capability of producing in these formats, embodied energy to actually produce thin section format materials, and high carbon footprint. An example, some of you may have seen this before, but I like to show these examples as to try to ground some of the research. This is a Tesla plaid electric motor, and it is actually pretty interesting construction. It's comprised of 529 stacked laminates that have this star shape there on the rotor, and the bottom picture there doesn't show all 529. It would actually take up the whole length of that shaft. But it's kind of interesting to think about, somehow those have to be produced. And the far right-hand picture here shows a thin strip of titanium that protects the leading edge, in this case of a Rolls-Royce turbine fan engine. And so these are examples of thin section format materials that happen to be very difficult to produce because of the alloys, in this case, an electrical steel for the electric motor or a titanium alloy for the protection strip. I'm trying to index my slides and the computer is sluggish, so I don't want to keep pressing the arrow button in case it doesn't advance. I don't know why it's not advancing.
Jim, the
Yes.
blade itself is made of what, as opposed to that coating?
The blade, yeah, the actual turbine fan blade is carbon fiber composite. So that's why the leading edge has to have a protection system. And I don't know why, but my screen indexing has paused. Um, so I apologize for having a technical issue right now, and I don't know what the reason is.
Perhaps you could come out of the presentation
Yeah, I'm going to
and
stop share and reshare. I
yeah.
don't know if it's some glitch on our internet is good. Uh,
You could mail the presentation to Eddie and he runs it from.
yeah, if it becomes a situation that's our best option, that's what I'll do. It's
The universal fix is turn it off and then turn it back on.
yeah, that's what I'm going to do now.
I mean, the whole
I'm
computer.
going to reshare. Going to reshare. I'm not used to these kinds of glitches, so I apologize. Let's see. Okay, we'll try it again. I'm leaving it in this format where it's not in presentation mode. I hope that's okay with all of you.
That's okay.
Because I can use the mouse and key down. So we've already been through these slides. So a little bit about this processing challenge and making these thin section format, in this case, metals, alloys. In the case of the electric motor laminate stack, that thin section star-shaped sheet that's actually punched out of a coil of electrical steel. So imagine 529 of those are produced to make one Tesla plaid electric motor. So conventionally, those are typically made from a 3.2% silicon electrical steel. And that electrical steel today is produced in a large capital investment infrastructure rolling mill. So this little cartoon on the right shows you kind of the size scale of a typical operation for making coiled steel sheet. And 500 meters is this arrow, and then there are all these operations that involve multiple rolling stages, multiple annealing furnaces, cold finishing, just an enormous infrastructure and a lot of embodied energy to produce a coil of electrical steel.
Recording in progress.
Oh, and so uh, uh, there's an actual limit in electrical steel production today. There is no commercial solution to produce at silicon content greater than 4%. And the reason that that's relevant is if we could actually produce at, say, 5% or 6% silicon, it would have a radical impact on efficiency of electric motors. But today, there is no viable route to do that by rolling. In the case of the titanium strip that's protecting the leading edge of this carbon fiber composite fan blade, the titanium strip itself, the cost of producing titanium in these thin section formats increases exponentially with decreasing section thickness. So it's a cost issue. It's extremely expensive to produce titanium in strips. So what could be done about this? This is really the basis of my talk, is using machining as a deformation-based process to produce materials. So what I'm going to do is show you a little video of a machining process. And in machining, the process itself is characterized by large strains, high strain rates, high energy dissipation, and involves severe contact conditions, in this case between a tool or die and the interface with the material. So I'm going to play this little video and
Well, I guess we're just going to have to wait.
Well, Peter, in a normal composite, you start with a fabric, basically. It has whatever shape you want, and then you could deposit the resin that holds it together. Now, his was a carbon fiber composite. So you start with a carbon fabric, presumably, but then how do you add the resin to that? I presume it's not a normal resin because that would boil off in these applications. So how does he fix that and stiffen that shape?
This is not a high temperature application. This is the ambient air temperature because that's a fan blade. It's not a turbine blade.
Okay, good. I'm glad you said that. I missed that part.
Yeah, it's a fan. It's one of these high bypass engines with a big fan blade on the front of it, and it's not a high temperature requirement.
And you still need the titanium protection?
It's running around in the sky, trying to defend itself against particles and debris. So yeah, the question I have is how long does it last? What's the tip speed? One of those kind of things. But that goes to the adhesive. But it's a protective, I presume, from airborne debris.
And birds.
Yeah, because that's the leading edge of the front of the engine.
It's always intrigued me exactly how they protect the engines because.
Okay, I think I'm back, everyone.
Oh, okay.
I have no idea why, but in this process of restarting PowerPoint, it dropped my link to you all completely. So I'm going to reshare and resume.
Let me see if I have to co-host you. Oh, no, I didn't need to. Very good.
I think we're back online. Does everybody see the picture again?
Not yet.
Not yet.
Okay.
Yeah,
you go.
yes.
Okay, so I just played this video. I'll play it again.
Ah, okay.
That is just an example of what we would normally call a chip made in a machining process. So you can see that in this case, it's kind of a strip. It kind of coils around. And so you could probably envision that it's making a strip. So we could probably take advantage of this process in a new way. And that's what this talk is about, is using this deformation process in machining as a way to produce materials. So in metal cutting, the process is essentially looking at it in this kind of simple two-dimensional framework. It's a cutting tool engaged with a workpiece, a material, and the workpiece has some velocity and it engages with the tool. The tool is removing some layer. In this case, it's on the diagram, it's labeled as T naught. And then that material passes through the shear zone and goes through a large strain deformation. And it also increases in velocity, and the chip, what we call a chip, then actually has it increases in thickness. This is the result of the shear zone deformation. So some key things here, there's the tool is often engaged at some angle we call rake angle. This is the shear angle. And in the metal cutting problem, one of the challenges is that this shear angle, the strain is not something we can just calculate. We actually have to know something about the process. We have to typically, for example, we could measure the forces in the process to get to the strain, or the velocities, or we could actually physically measure this deformed chip.
But the diameter is changing as you cut, so you have to figure that one out too.
Yeah, this is another. So going back to this picture, as this tool is plunging into this part, there is a change in the diameter, and so the velocity is changing. But there are ways to actually, in modern machinery, we can actually compensate for that by controlling the rotational speed of the workpiece.
Okay.
But we often, in our research, we actually look at the metal cutting process as a large strain deformation platform, and so we can actually study what's happening in this cutting framework. And so we do that by using high-speed digital imaging. We set up a cutting experiment where we can look at this cutting process from the side, so to speak. And we can capture images. It's pretty amazing what we can do today with modern digital image technology. We can capture these images at high speed. And then we can use what's called digital image correlation and actually find the strain directly from the velocity field, so, and the strain rate as well. So it's pretty amazing. We can do this by direct measurement. And so I'll play this other short video just to show you what happens. This is an example of happens to be a copper workpiece. The cutting tool's on the right-hand side here, and this is the chip forming across the cutting tool. And I don't know why I'm having such a difficult time with the mouse. But you can see these streak lines that are embedded here over the digital imaging. You can see that the flow of the metal through this deformation zone involves a lot of what we call sinuous flow, because these smooth streak lines on the workpiece, you can see how they begin to go through the shear zone and take on a very sinusoidal or sinuous demarcation. So that's what happens in the metal cutting, and we study the process from that perspective. And some of the interesting things about metal cutting, it actually also informs something about the microstructure of the chip. So for those of you that are material scientists, you can appreciate that the typical metals and alloys have some bulk microstructure. It's often micro scale in terms of the size of the grains, micron scale. But the chip itself, and this is on the right-hand side, this is just a conventional metallography, in this case of titanium being cut. And you can see that from an optical microscopy perspective, that there is really nothing you can observe in the chip. And that's because the actual grain structure of the chip is now refined below the resolution of optical microscopy. So that's an interesting other aspect of the large strain and machining, is that we can now not only use it as a potential way to make materials, but we can also actually use it as a way to control the microstructure of those metals and alloys in a new way. And that's what this slide is showing a range of the microstructures and conditions that can actually be achieved through machining. By changing the parameters of the machining process, the velocity and the rake angle of the cutting, or the shear angle, we can actually map a whole range of shear strain and deformation rates and essentially create different structures, different grain structures of the, in this case, chip. And so then we've demonstrated how we can create twinned microstructures, bimodal microstructures, even recrystallized microstructures, just a whole range of capabilities, all through the parametric control of the machining process.
Where
And
do you
actually
want to be?
accomplishing
Where do
types
you
of
want to be on this
microstructures that
diagram?
really aren't, they're first of all not available to conventional manufacturing processes, but also in some cases we're accessing microstructures that can only be produced using the taking advantage of the metal cutting process. Another aspect of what we're working on in our research today is exploiting embrittlement in cutting. And this video is an example of liquid gallium exposed onto an aluminum workpiece. And the gallium actually absorbs into the workpiece and has a drastic influence on the deformation mechanics. And so I'll show another video. And this is normal cutting, and then it's approaching the air. So now it's approaching the area where the gallium is. Now you see the radical transformation in the cutting process. And I'll replay that. So this is normal cutting. There's no gallium on the surface of this workpiece. This is an aluminum workpiece. And then the liquid gallium is applied, and you can see what happens to the cutting. So this is an example of global embrittlement caused by gallium. It's actually a fairly well-known phenomena. But what we, several years ago in our lab, this is work together with my colleagues at Purdue University, as well as Indian Institute of Science and Indian Institute of Technology, have begun to explore is what happens in adsorbent induced effects. In this case, surface stress that is on the surface of the workpiece. And this is an example where these so common inks and adhesives, benign media, can actually be used to embrittle the material. And so on the left is another example of cutting, and on the right is tracing the force in cutting, and it's bare, and then it hits a surface that has a thin layer of, in this case, an ink or glue, a thin layer of media. And you can see that what happened is not only a completely different type of morphology of the chip, uh, but the actual deformation zone changes, and the force required for the cutting itself drops by nearly half, simply by having a thin layer, in this case, of a benign media on the surface. So this is an interesting phenomena that we've been exploring and understanding how we could leverage this in this overall approach to materials processing by machining. It can even be done using self-assembled monolayers. So a monolayer of media, an organic media, and this is another example using this videography or high-speed imagery. You can see on the left is no self-assembled monolayer. On the right-hand side happens to be with stearic acid as a monolayer. So you can see the drastic effect it has on not only the shear, but the morphology of the chip itself. And we're studying what happens at different chain lengths of these monolayers. And it turns out that there's a critical chain length of, in this case, 6 for a hydrocarbon chain where the effect becomes relevant. So we've been studying different media, inks, alk oxide effects, alcohol. And recently we've actually explored these surface stress effects in a very interesting macro scale experiment where we take a simple cantilevered beam strip of aluminum, and then we present one side of the beam, in this case with a hydrocarbon, and we can actually measure the deflection. The beam, the surface stress on the beam actually creates a deflection that we can measure macroscopically in the beam. So these are interesting areas. And so what I'll talk now is about the bulk manufacturing of materials. And going back to this problem I mentioned earlier, in the steel coil manufacturing business, it's a very large scale, expensive endeavor, and it's only capable of producing steels that have about 3.5% silicon. So, and then the high cost of doing this in something like titanium, for example. So there's an opportunity to overcome the obstacles in rolling by using metal cutting. And so what I'm going to show you right now is what we call hybrid cutting extrusion. And in hybrid cutting extrusion, we take this otherwise conventional metal cutting process and we add an additional constraint. So on this right-hand view here, there's this constraint added. You could think of it as another tool directly across from the cutting zone that causes the chip to now be extruded at the same time that it's being cut. And the one thing I want you to notice here is that the chip itself, the thickness of the chip is being controlled a priori. It's being predetermined. And it's smaller than the chip thickness that occurs in the normal, what we call free cutting. So we're actually constraining it, and this is just a simple view of that. And so by adding this constraint, we're now able to control the strain, or lambda. We're able to control the shear strain directly by controlling what's happening to the chip thickness. So the strain itself can be expressed as a function of the rake angle, alpha, and what we call lambda, which is the ratio here of the chip thickness to the uncut chip thickness. So we can directly write an expression for strain. And why this matters is that we can use this process in a single step. We now have a design handle to produce metal strip directly. We can impose significant strains in a single pass so that otherwise strains or the process of producing rolled sheet, which often takes multiple rolling steps, sometimes 20 or more, We're doing it in one step. And so this all informs a machine design approach to how this could be accomplished. So we now have the ability to make a strip directly by controlling the rake angle of a cutting process, the chip thickness ratio directly because we can set that a priori, and the speed. So we have these three parameters and we can build a machine around this. So that otherwise scaled plant of, say, 500 meters of infrastructure that's required to produce coiled, flat rolled sheet steel, that process can actually be simplified into a framework of a machining center, a conventional machine, CNC machine, by configuring it with this hybrid cutting extrusion. And that's what these images are here on the bottom right of this slide. It's showing taking this hybrid cutting extrusion process and putting it into an actual engineered framework. So how this works, there's this set of tools, a cutting tool and a die across from it. And it's installed in the machine axis. And in this case, I'll show a short video. The axis just simply moves and the tools are engaged in the workpiece and literally cut a strip directly from a bulk workpiece. So in this video, that workpiece happens to be copper, which is, and it's 100 millimeters wide. And on the screen here on the far right, you see a picture of that copper strip and a reminder of what the star-shaped electrical steel piece looked like. We're able to make in a single step of processing a sheet of, in this case, copper that has a similar size, similar thickness as the electrical steel part that's shown right there. So we're on our way to making to doing this. We've done this in electrical steel, but just not at this size scale. We use the copper as a way to demonstrate this. And the other thing that's interesting about this is because we have the ability to control the microstructure now, we can actually inform unique microstructures by using HCE. This just shows that an example of one of the copper strips, and this is using EBSD to look at grain size and grain texture. And then we can do this also broadly across the range of metals and alloys using transmission electron microscopy. We can show that we're actually producing, we can produce materials that have ultra fine grain size, or what we sometimes call nanostructure. So I may come back to some more examples of that. But now I want to talk about how we can use machining to produce metal particulate.
Can we ask you a
So
question?
in the conventional machining process, the tool is typically engaged with a workpiece and a chip is produced, which I've shown you several videos of that. But if a superimposed oscillation is applied to the otherwise continuous process, it's possible to divide that process into a series of discrete cutting events. And in the case of conventional cutting, the tool is engaged and a continuous strip is forming. But in the case of modulation assisted machining, that otherwise continuous cutting is now divided into a series of discrete cutting events simply by superimposing a controlled motion onto the process. That's what MAM is. And MAM can be used in a framework like that's shown in this set of photos. This happens to be a commercial MAM system and happens to be something that the company that I co-founded commercialized in the early mid 2000s. We began selling these systems for drilling operations, which I won't get into today, but that same MAM technology that is used for drilling systems can be used in a process to try to make chips. And I'll show you, this is just another video example. You saw it was making a strip a moment ago. And then when the modulation was turned on, it began making discrete chips. I'll play it one more time. You see the ribbon, and then the small discrete chips form when the MAM is turned on. So that can actually be harnessed in a new way to actually produce metal particulates directly using this modulation assisted machining. So we're able to produce these unique morphologies that actually can't be easily produced in other conventional ways. We have generally three categories that we refer to: equiaxed, platelet, and fiber. And you can see these are SEM images, and you can see from the scale bars that these equiaxed structures are similar in size scale to what otherwise might be referred to as gas atomized metal powders, which are typically spherical or blocky. These are actually more blocky, and they're not spherical. And the platelet is actually an extended version of an equiax by changing one dimension. And then finally, the fiber is kind of at the extreme end of producing these discrete particles. And so today, the fiber manufacturing technology has been commercialized in commercial domain. But our company has been working on some new applications of this, and some of the research we're doing is looking at new opportunities. But so in making the particulates, we can control the morphology, the size and the shape. The rate of production is directly related to the frequency of the oscillation that's imposed on the process. Unique textures of the actual surfaces, and I'll go into that in the next slide. And again, this ability to control the microstructure of the metals in a new way. So here's a little bit more about the morphology of, and this happens to be the fiber. And some more SEM images. The fiber has a unique cross section. This is shown here in the inset. We refer to the cross section sometimes as being triangular. It's definitely not round. It's not anything like a conventional drawn metal fiber. And it has actually some really unique surface topography as well. On one side of the fiber, the side of the fiber that was made by engagement with the cutting tool, it's actually very smooth. And these are optical graphs from profilometry, so optical profilometry, just showing you comparative scale. The other side of the fiber, you can see, has this interesting corrugated texture. And the one thing I want to point out that's also quite interesting is on the smooth side, I don't know if you can see my mouse is moving on the screen, but on the picture number C, which is the middle row at the top, it has the characteristic of the smooth side has little lines that are actually the feed lines created by the edge of the cutting tool. And then the back side of the fiber is the free side of the fiber made, and it actually has the orientation of these corrugated lines. The orientation of the lay is actually in the opposite direction of the actual fine lines on the smooth side. So just some interesting morphology. And so we began to think that, there's something unique about this. How can we take advantage of these fibers in a new way? Well, we decided that what we could do is use them in a new composite structure, a composite system. And so we began to produce thermoplastic filaments that could be used in additive manufacturing or 3D printing. So we refer to this as a new class of high-performance composites, where we merge the capabilities of modulation assisted machining to manufacture the metal fiber, and we are able to use the fused deposition modeling or 3D printing process as a way to make a new composite structure. And this slide just shows a simple laboratory framework. We take metal fiber and combine it with thermoplastic pellet. We extrude that into a composite filament, and then we 3D print, in this case, tensile test samples or any sample we prefer to produce. We're exploring what the microstructure or the structure of these composites looks like. In this case, using CT imaging is a good example. Doing some comparison of commercial composite structure made from 3D printing of carbon fiber compared to, in our case, metal fiber. And then obviously continuing on with the tensile testing of these dog bones, looking at the actual mechanical properties, trying to understand what is the benefit of adding this metal fiber. And one of the things I want to point out to all of you is that in the tensile test response, this dark black line, that's the base. In this case, it's PET-G polymer, but it's the base PET-G. But look at all the other composite formats have much higher modulus, much higher ultimate strength, just a kind of remarkable result for the actual first published results in this space. It's really original work. There's really not too much for us to compare to out there in terms of metal fiber in this size scale. There are obviously compared to the carbon fiber. So I'll point out to you the orange line is the carbon fiber, which any of us in composites, we would always obviously expect carbon fiber to outperform structurally. But the one thing I wanted to point out is that the 30% by weight aluminum metal fiber actually has a very comparable, in fact, a little bit higher modulus, which is relevant from a design perspective uh, because we designed for systems to operate in the range of elastic compliance. And then an interesting artifact of the tensile testing is that the PET-G goes from a ductile failure type of mode to a brittle failure mode. That's what those images are from the SEM. And then hardness, you can see with increasing the fiber percent by weight content, the hardness increases and actually exceeds that significantly over carbon fiber. And then the wear resistance, the actual wear behavior of the 30% by weight aluminum fiber actually outperforms carbon fiber. So these are interesting results that we're pursuing to understand more about not only the mechanical properties, but we also are doing some work now to understand the physical properties, including things like thermal and electrical conductivity, looking at potential application domains. Why is this possibly relevant? There are a whole range of thermoplastic uh, components across multiple industry sectors. I'm just happening to show you one of them here. This happens to be a orthopedic hip implant from Smith and Nephew. Today they use a high density polyethylene bearing. And I'm showing you this just to get you to think about, where could a high performing composite polymer that has better wear performance, where could it operate? Where could it have an impact? And this is just an example of something that we're actually looking at right now. I'm working with some researchers at Rush Medical in Chicago to discuss these kinds of opportunities. And then from a maybe more interesting or kind of fun perspective, looking at this additive manufacturing is taking advantage of new performance characteristics, the strength and wear resistance. An interesting aspect of 3D printing is mechanical design capabilities, and this happens to be a skateboard. And some of you might be surprised to know that the market for wheels, which is what we're making in this picture, and I'll talk in just a moment about that, is surprisingly in the United States alone, it's a $2 billion a year market, the wheels of the skateboard. So we're actually producing a metal fiber composite skateboard wheel, and we can control the geometry of the skateboard wheel in new ways that could not be done, they're not done today because the manufacturing methods don't accommodate it. We can actually create unique geometries that inform different elastic response of these wheels. So you can actually create wheels that have different response to the rider. So I'd like to thank all of you for your time. This is by no means an exhaustive list, but I wanted to mention some of my co-principal investigators today. Devapriya Mohanty, Brian Arnold, Aniruddha Dupa, Rashid Mosabe, Bala Rao, Kaushik Viswanathan, Jennifer Kustis, Andrew Kustis, Tatsuya Sugihara, Kevin Trumbull, Professor Lataniason, and Professor Chandrasekhar at Purdue. So thank you all for your time. I'd be happy to go back if there is any additional time. I could share a few slides that I didn't get to discuss on the strip making, but I know we had some technical glitches, and I wanted to make sure we had time for questions.
Well, thank you, James. I have to admit that I always thought of machining as something that was done and gone. And I think what you've shown is an extraordinary open field of research and potential. And I'm quite actually taken by what you've achieved. And speaking as a guy with a 3D printer, I look forward to seeing all kinds of new fibers and materials available. But one of the questions I have is with the impact that your technology has or could have on machining seems to be quite dramatic. And I wonder if you could just speak a little bit about how you see the this technology actually being implemented in industry and what the effects are. It seems enormous. You can change a 500-meter assembly system down to a few, 5-meter, 10-meter thing. That's an enormous efficiency gain.
Yes, that's actually a key point that I often talk about is that, and I'm showing this picture on the screen right now is to show all of you that this machine is showing in the building here in this kind of second picture, that we can produce a strip that is the size scale needed directly to produce, in this case, the star-shaped component for the Tesla Plaid. We could actually produce that at the point of use. Like we don't need to. It totally changes the whole supply chain perspective. Whereas today, for example, the whole industry is really constrained by, and I'll show this picture, this production of these metal coils, which often have to be produced sometimes more than a year in advance. So the industry, the users of the people producing electrical steel or electric motors using steel laminates. So not only are we capable of producing this or processing this material directly at the point of application, so at the motor assembly point, we're able to also deliver a process that can produce it in a high silicon format. So there are two things. One is the manufacturing system level improvements in terms of cost, infrastructure, lead time, supply chain perspective. But we have the ability to now access alloys that can't be accessed by conventional processing. So there's like a product performance application or performance gain or benefit to this. It's very remarkable. The motor industry is around a $30 billion industry just for electric motors, and that's just for that's just for these motors that are in this range of like the Tesla Plaid. There's a whole nother range of electric motors used across consumer markets, things like air conditioning motors, even transformers use this kind of stacked laminate type configuration. So there's a huge potential impact for industry, but also this idea of scale of manufacturing. So a new way to process something that totally disrupts what we would otherwise maybe call an entrenched industry of rolling that we've been doing for more than 100 years. I'm not suggesting that this process will overcome rolling used broadly for, say, automotive sheet steel used to produce body panels in cars and aluminum panels in box trucks and things like that. This is an interesting application of machining to address these niche areas that have this either a technical barrier of, in this case, achieving a higher silicon content, and simultaneously changing the whole supply chain economics. And similarly, on this leading edge strip is another example. It's low volume. It's difficult for plants to manufacture these strips because it's very costly.
What is the critical enabling technologies that allow you to make these changes?
Yeah, the critical enabling technology here is in the strip making, and I'll go back to this diagram. The fundamental critical enabling technology is the hybrid cutting extrusion. It's the addition of this constraint to actually control the metal cutting process now as a strip making process. But
But it
then,
seems like photography or imagery is a big part of that, right?
well, the image analysis that I've been reviewing, that certainly opened the doors for us to understand. You know, we had to understand the fundamentals of what happens in the strain and cutting.
Right.
And this is a problem that in my research sector, many of us have been researching. You know, I've been researching this now. This fundamentals of metal cutting has inspired my research now for almost 40 years. But it's not a new problem. But we have these new techniques and tools to actually characterize the problem even in a way that we didn't have before.
Yeah,
Yep.
I will think as an EMC when additive machining additive systems came into being, and we were able to manufacture parts that would have taken us months to get. You know, stupid things like racks that were missing a component or broke or something like that, we could print almost instantly. And it changed our whole manufacturing capabilities in our assembly plants. I do want to go on though to other questions. Jenny has her hand up and has waited very patiently for a while. So Jenny.
Hi, Jenny.
Yeah, thank you. And there's a high strain rate for making strips. What kind of uniformity or level of uniformity of deformation can be achieved? And how to make sure that can be repeatable and also be consistent?
Yes, good question. So I'll go back to, let me go back to this slide. So because of the placement of the constraint in the hybrid cutting extrusion, the process becomes very repeatable. It's a process that's now constrained. We're controlling the shear angle and the thickness directly. And in terms of the strain rate, it's a matter of speed. So this velocity is what directly controls the strain rate. Obviously, the strain is relevant too, but it's all controlled parametrically by, in this case, geometry of the process, geometry and the fundamentals of the process, the speed. But you asked about the consistency of for example, the microstructure. And I'm just going to this as an example. This is showing the EBSD in this case of the copper. I could produce this copper strip over and over again, and it would have the same texture, the same microstructural texture, same size, same structure. If I change the speed of the process, that might change the actual grain structure. So going back to the map, I'm controlling the shear strain and the deformation rate.
Okay.
I can decide which of these structures I want to achieve.
Okay.
And that is repeatable.
Okay. How about at a given set of parameters, machining parameters, what's the uniformity across the strip?
Oh, so like through the thickness.
Locations?
Yeah, let me show you. Let me show you a picture I didn't show earlier. And it's a good question. Okay. So Here's a series of images here. This happens to be a strip of aluminum and picture A. And you can see the series of images on the right-hand side. The first image is what's called HCE. That's hybrid cutting extrusion. And so you can see there, you're asking about the uniformity through the thickness. You can see at the edges or at the strip walls, if you want to call it that, the top and bottom of the strip, the actual texture has the actual shear imposes a little bit of a flow orientation at the faces of the strip. And as that strip is rolled, you can see that gets a little bit more pronounced. But it's a very subtle change in the shear flow at the faces of the strip. And that's actually something that I don't have the pictures here to show you, but by imposing different conditions of the position of the constraint tool, we can actually create different hydrostatic stress states. And it can actually change how consistent it is across the thickness. But this shows an example of it's generally consistent, not 100%, but at the strip edges, there's a little bit of a difference in shear flow. But the thing that's maybe more important to take away here is, and I don't have a picture of normal rolling here to show you, but the normal texture orientation in rolling is in the direction of rolling. And that's the only direction you can achieve in rolling. But in this metal cutting configuration, using hybrid cutting extrusion, we can actually influence the orientation of the microstructure, the orientation of the shear. So we get these different shear flows. But these are strip. This is showing what happens when we roll that strip. And you can see that the orientation of the shear flow begins to go in the longitudinal direction. That's just the result of rolling. So pictures B, C, D, and E are taking that strip and rolling it through subsequent rolling steps. But rolling has the characteristic orientation that's always in the rolling direction. That's actually a limitation of the rolling process as well. It does not have the ability to actually control orientations in the way that HCE does.
Okay, thank you.
Albert.
Jim, very nice. And I'm glad you emphasized the importance of that constraint, because without it, the other side of that strip didn't look too good in your pictures. And I presume it's because the stress wave reflects off an open surface, so you get a refraction wave, and that's kind of really ruining the structure of the backside that is not constrained.
Yeah, if it's unconstrained, and I don't recall if there's a good picture here to show you what the surface looks like. I'm looking to see. I mean, a typical video is an example. You
Not
can
so
see,
good. Yes.
yeah, it's not good at all. In fact, going back to the original video I started this presentation with and talking about this cutting process, that is what inferred everything that I've been talking about, but that strip would be a very poor quality strip on what we would call the free side. The roughness would be very poor and not acceptable.
Correct.
So that's one of the key elements as well of the HCE process is it controls the strip thickness, but it also infers a finish. And I was going back to this picture I didn't get to show you that we compare these finishes often. It turns out that there's subtle differences between the constraint side and what we call the rake face side, but they're both better than a conventional rolled surface.
I never put it at a.
So the strip itself has both sides are smooth and both sides have surface roughness that's better than a rolled surface.
Okay. And I understand the importance of additive manufacturing and 3D printing, and you fit right into that. But my question is, purely from an energy point of view, how would this process compare to just standard rolling on a per square foot basis?
Well, I don't know that I can directly answer that question in terms of I would have to be able to make the comparison one-on-one to the same size requirement, the same volume, the same. What I can say, here's all I can tell you is that the infrastructure required to produce the electrical steel, you saw what that looks like as an example of making these steel coils. All we need from that is this small star-shaped part. Okay, and so today to make this small star-shaped part, we're producing these giant coils, and then the coils have to be stamped and produce the small scale part. We're able to produce the size scale of part needed today in a infrastructure instead of being 500 meters in scale and the cost associated with that in the tens of millions. We're doing that in one machine that only takes up 5 square meters and costs in the hundreds of thousands.
But you still have to stamp it.
It still has to be stamped, yeah, and that could be done in line as well. That's another. At the end of the day, the motor manufacturer today, they have to get the coil and they bring it in house and then they have to stamp it. Well, they're using the format of a coil that might not be optimal for their actual size of their stamping. And so there are yield effects too. There are yield losses that occur because they're stuck with making it from a, say, in this case, maybe a 48-inch wide coil. Whereas the HCE process can produce the width of the strip to be optimal for what's needed to stamp the part. So the losses due to the yield are reduced.
Understood. And of course, the difference in equipment, machinery is remarkable. But could you, just from the final state of the deformation, back out how much energy went in? And you're saying it's not quite the same.
Yeah, so I don't have that slide in this presentation, but the total energy dissipation to go back to this, the HCE process, the total energy dissipated to produce the strip is about 1/3 of the energy dissipated, or you could say consumed, in making rolled strip. So that was actually an analysis we did with our partners at Oak Ridge, and there's a report on this, but the total energy is about 1/3. So that's another remarkable impact. I mean, that goes back to this carbon footprint, total energy consumption, simply because we're doing this in a single step. Whereas the normal rolling process is a whole series of accumulated deformation steps that have significant energy, as well as the annealing processes that are actually consuming significant energy in between the rolling steps. So we're not doing any of that annealing. We're not using the furnaces and so forth to create the strip. So it's a very good question, and that's actually something we've written several. There's some publications we have on this. There's some reports we have on this about the total energy dissipation.
Very nice. Thank you.
I'm just wondering, how wide a strip can you print or can you make without losing efficacy?
Yeah, I mean, the only limitation in the width is power. So this strip making process by HCE, and I'm showing here something that was 100 millimeters wide. The other beautiful thing about this HCE process is you can use first principles directly to determine what the machine design element should be. It's very interesting in that sense because there is no limitation. It's a matter of how large of power can you put behind the machine. How big of a machine is needed. So for example, if you asked me, could we produce a strip that was 1,000 meters wide? It simply is taking this machine design configuration and scaling it accordingly. And I've worked around machines in the aerospace industry that are built into the foundation of the facility. Huge. So it's not unrealistic. I've even seen machines that have 500 horsepower motors. This machine that is cutting this strip has a 10 horsepower motor.
And I assume that by scaling down, the manpower required is a lot less than the maintenance as well, I would think.
Yeah, it's just a remarkable way to look at how this technology could disrupt something that's an otherwise entrenched industrial process from all kinds of perspectives. Engineering, maintenance, flexibility, ease of relocation, infrastructure costs, time to build, in other words, time to bring a plant online. That just a whole interesting range of things. And at the end of the day, it's based on a fundamental cutting process that we've known that metal cutting is very well known today in industry in terms of characterizing tool life, when to change the tools. Of course, there will be these kinds of things in the process. The tools would have to be changed at some interval. But these things are all very engineered. It's very accommodative to engineering principles.
What material
Jim,
do you use?
on the point of scale up,
Yes.
If you really want to get large width, like Eddie's asking about, then you have to rotate a huge initial piece.
Well, here we're not rotating the workpiece at all. That's the whole point.
You're just advancing your cutter.
Yeah, that's what's happening. We're just cutting the strip directly from a billet. So we're able to produce the strip directly from, it could be a casting, a forging, a billet. It's not rotating. Now
So
there are some configurations where we have rotated and for a different reason, but this strip to make these sheets is a discrete process.
So all the photographs you showed us is for a non-rotating case. Is that correct?
Not all of them. There were a few that for example, this is rotating. This is making a coil. So this is a coil of aluminum. These are small coils these are Inconel 718. This is a wire. This is a copper wire. This is the coil unfolded or unrolled here. So the HCE process can actually be introduced in the case of a rotating workpiece to make it a somewhat semi-continuous process to make, for example, a really long strip.
Mm-hmm.
This could be used, for example, to make the strip needed for the leading edge protection system on the Rolls-Royce turbofan engine that I was showing. But in the case of the star-shaped part needed for the electric motor, it doesn't need to be a rotating process. There are many advantages for it to be this discrete process like this. But you're right, if it was huge, if I needed to make a really long strip, like hundreds of meters, that's not practical for this configuration of HCE. We would look at the rotating system, and then yes, you have to accommodate something that might be rotating, and it could be large, but it's all possible. That's an engineering problem.
Thank you.
Okay, I think we're reaching the end of our time. And I'd really like to thank James for giving us a presentation of what looks to me like a tremendously disruptive technology. I look forward to hearing more about it. Actually, I would have liked to have heard a lot more about the drilling capabilities.
I'd be happy to rejoin you. I'd be happy to rejoin your group at another time and do that.
Yeah, because I'm kind of interested whether it has applications into advanced geothermal uh, drilling, for example. I don't know if that's something that you have considered or has been considered.
We actually have a proposal in with colleagues at Ames and at Sandia to the DOE directly for application for these site investigations for rare earth elements to actually improve the core drilling processes using aspects of modulation assisted machining.
Well, I'll talk to Ron and maybe we'll have you back.
Yeah, that'd be great, and really appreciate everyone's time today. And my apologies for the technical glitches. I don't have any excuse.
It's not your excuse to make. I think that might
it happens.
To Microsoft and others.
Yes, I guess we thank them for that, and
Yes.
be glad that we're not traveling on the Artemis and have. I've understood they have some issues of some kind related to this, but at any rate,
dear. Okay.
thank you all
Let's
so
hope-
much. Thank you all so much for your time, and appreciate it, all of your questions. And please,
Thank you,
please
Ron.
don't hesitate
Thanks.
to
Yeah.
email me if you if there's some offline question of interest. Please email me.
Thank
I
you.
will.
Yep.
Thank you very much, James.
Yep. Cheers, everyone.
Yeah. Bye-bye.
Cheers.
Bye.
Bye-bye.